7.5, the sum and difference identities. So first off, let's just quickly remember that cos is x over r, sine is y over r, tan is y over x, because we're going to need those this unit. And these are all of our sum and difference identities. So there's a whole bunch of them, and we'll just use them as we go. Okay, given angle A, alpha, in standard position with its terminal arm in quadrant 3, and knowing that cosine of A is negative 3 over 5. So let's just start there. So let's do alpha. So it is in quadrant 3. We need to find our x, our y, and our r values. So because it's in quadrant 3, our x value is going to be negative, our y value is going to be positive, and our r value is going to be positive. It also tells us that cos of alpha is negative 3 over 5. So that is my x and my r values. So we're going to say that x is equal to negative 3 and r is equal to 5. So what we need to do is we need to find y. So I'm going to use Pythagorean theorem. Wow. So I know that x squared plus y squared is equal to r squared. So I know that negative 3 squared plus y squared is equal to 5 squared. So I'm going to do the square root of 5 squared minus negative 3 squared. So what I get from my y value is y equals the square root of 16. So y would equal plus or minus 4. And we'll use reasoning to decide that it's actually plus 4 because we are in quadrant 3. Alright, so using that, now I can find sine of alpha. So sine of alpha is going to be y over r, so 4 over 5. So we're going to table that for now, and then we're going to come back to it. Alright, now we're going to do beta. So beta is in quadrant 2. So because it's in quadrant 2, I know that. Okay, pause. Going back to this one, sine was in quadrant 3, so y should have also been negative. My bad. I thought I was looking at the next one already. So sine is also going to be negative 4. Okay, in this one, x is going to be negative, but our y will be positive because it is in quadrant 2. Remember that r is always positive. Alright, so now we're going to use the fact that we know that the sine of b, or beta, is 1/3. That tells us our y and our r values. So y is 1 and r is 3. So we're going to use x squared plus y squared is equal to r squared, and I'm going to skip the steps. We're going to go 3 squared, subtract 1 squared. So r is equal to plus or minus the square root of 8. I can simplify that radical. That radical can be simplified to be plus or minus 4 times 2. And I can take the square root of 4 to make it 2, and I'm left with a root 2 under the radical sign. So because it has to be a negative, because it's our x value, we're just going to write it as negative. So we have negative 2 root 2. So this will help us now find cos of beta. So we know cos of beta is negative 2 root 2 over our r value, which is 3. Now we want to find the exact value of sine of a plus b. So we're going to expand it by using the sine of a plus b. And I have run out of space, so I'm just going to erase some stuff. Okay, so I'm going to expand that to b. So sine of a times cos of b plus cos of a, sine of b, and now we're going to use these to fill that in. So we know that sine of a is negative 4 over 5. So we're going to just write it as negative 4 over 5. And then we know cos of b is negative 2 root 2 over 3. And we can just replace it with that. Cos of a is negative 3 over 5. And sine of b is 1/3. And then we're just going to simplify. So we have negative 4 times negative 2 root 2 is 8 root 2 over 5 times 3, which is 15. Negative 3 times 1 is negative 3 over 15 is 15. So this simplified final answer would be 8 root 2 subtract 3 over 15. And that is my exact answer. So remember, when it says exact, you want to be using these ratios. Okay, example 2. We are just going to simplify where possible. So the first one, we have sine of 8x cos of 3x minus cos of 8x sine of 3x. If we look, that is the same as sine of a minus b. So we can go sine of a minus b. Our a value is going to be 8x. Our b value is going to be 3x. And by a and b, I'm actually meaning alpha and beta, but I'm still going to say b, because I will forget every single time. So we have sine of 5x, and that's the end. We can't go any further because there's just no answer. It's just a variable. Okay, looking at the next one, what you should notice is it's the same as this right here. So we're going to use tan of a plus b. Our a value is going to be pi over 6. Our beta is going to be pi over 2. So we have tan of pi over 6 plus pi over 2. 12, that's a 12, not a 2. So we're going to combine those fractions. So I'm going to rewrite this as 2 pi over 12. So I have tan of 3 pi over 12, which is tan of pi over 4. And I'm going to notice that I have pi over 4, which is something that is we can solve, because it would use the 45-degree angles. So our 45-degree triangle is 1 run root 2. Our opposite over our adjacent is 1, so the answer to this one is just 1, and that's done. I ran out of room. So you can solve further if you have actual numbers. Okay, last one. Prove this identity. Sine of pi minus x is equal to sine x. So we're going to solve. I just realized there was nothing on the screen. I'm sorry. There we go. We're going to change this side. So we're going to go sine. We're going to use the subtraction formula. So our alpha is going to be pi, and our beta is going to be x. Wow. So it's going to be sine of pi times cos of x, subtract cos of pi, sine of x, and it's going to equal to sine x. So let's bring out that unit circle, because we can evaluate sine of pi. So sine of pi is over here, and it's right there. So sine of pi is actually 0. So we have 0 times cos x, and we can evaluate the cos of pi, and it's negative 1. So negative 1 times sine x equals sine x. Get rid of this. So right here we have 0, so that's gone. And then we have minus negative 1, so that becomes a positive. So sine x equals sine x. Amazing. We're done. That's the end of the proof. You're all doing amazing, sweeties. Okay, that's it. Bye.